Online labs are not useful if you want to learn. That's the problem. No one wants to learn from an online lab.
Right, they're like, oh, we in a regular lab, you have to build this system, but it starts to run the simulation. It's like, cool.
That's exactly what did I learn? That's exactly what I do. Is in lab, you guys need to know that phosphoric acid is viscous, but for you guys, it doesn't matter. It's like don't pour 95% phosphoric acid.
Okay. So homework today, right? I believe, I don't know if anyone who's on Zoom right now has tried to submit theirs online. I think I set it up a while ago. Hopefully it's there and you can submit it. I don't know. But for the end of the Zoom session, if someone here has tried to submit their homework on Zoom and has had issues, let me know. I'll fix that. But set it up a week or two ago, and I just pretty sure I set it up fine. So, all right. So yeah. So any kind of questions before we get going today? Anything? All right. So today we're going to kind of start our last of two topics for the semester, right? Electrochemistry. And then after this, we'll talk some about statistical thermodynamics in kind of the last week. So yeah, and then after that, it's just reviewing for tests and taking tests. Fun stuff. So yeah, so electrochemistry, hopefully we remember some of this stuff. Again, I always forget what's taught in other chemistry classes besides Gen Chem. But maybe you've seen it outside of Gen Chem, maybe you haven't, right? Let's just kind of review and remind ourselves, right? So an electrochemical cell, right, is just kind of the, the picture of what I have here, right? This entire set of stuff is a cell, right? It's the, the device apparatus, right? What you set up to run your electrochemical reaction, okay, your redox reaction, right? You have electrodes, right? What would be the electrodes in this picture? I guess it's labeled. That's not really much. Yeah, zinc and copper solid. I forgot that it's labeled in the picture, right? So you can read, you can see. It's zinc solid, copper solid, right? The electrodes, right, is some sort of metal, solid metal that's inserted into the solution, right? That conducts the electrons from the anode to the cathode, right? The electrodes do not have to be directly involved in the electrochemical reaction. They can be some sort of like an inert platinum electrode that's not going to do anything to the electrochemical reaction. Now, it might help catalyze the reaction, but it itself, right, is not being consumed or created, right? While in the electrochemical cell presented here, right, the copper electrode and the zinc electrode, right, are going to be changed as this reaction goes, right? Because as the reaction goes, right, at your anode, you're oxidizing that zinc to Zn2+, so you're losing some mass from the zinc electrode, then you're going to gain some mass from the copper electrode as you have that copper 2+ getting formed a copper solid, right? So the masses of the electrodes in this electrochemical cell will change because they're involved in electrical reactions, right? But they don't have to be for an electrode, right? Electrolytes are then your ions, right? Your zinc and copper ions and things like that, right? Involved in the redox reaction, right? And don't even have to be involved in the redox reaction, right? the nitrate ions, sodium ions, right? Those are also considered electrolytes, right? Now those are spectator ions in this reaction, right? And are there to balance the charges in your solution, right? And to do that, you need some sort of salt bridge, right? Some sort of connection between the anode and the cathode to allow these cations and anions to flow, right? The anions flow to the anode, cations flow to the cathode. Right, that's why you have cathode, cations, right? Anode, anion, right? So anions flow to the anode, cations flow to the cathode in your salt bridge, right? And the reason, right, an electrochemical cell is set up like this, right, is because if you just mix everything together, right, the redox reaction would occur, right, but it would just occur within that solution, right? But if you set up your redox reaction like this, right, these electrons have to pass through something, and as the electrons are moving through this wire and moving against some sort of voltage, some sort of potential, you can extract work, right, extract electricity, right, get power out of this electrochemical reaction, right, as it's going, right? Hence, right, how a battery works, right? I mean, you can short your battery if you were to connect directly, right? If you bypass, you know, where your, you know, the ends of your battery, right? You can imagine like this is a battery, this is, you know, the, you know, top side, this is the bottom side of the battery, right? You plug it in to some app, you know, your remote, right? And it connects these two ends, right? You know, electrically. Now it allows the electron to pass from one to the other, and as the electrons are passing, right, you get power, you get charge, right? You get some power from electrochemical work. Okay. But if you were to bypass that connection, right, and just directly open these things up, say within the battery, right, and connect these things within the battery, right, you wouldn't get any work out because the reaction would just take place within the solution, right? And so, and that's why, you know, we create these electrochemical cells, right, is to get out some type of electrochemical work, right? Okay. And again, salt bridges need to maintain neutrality in those solutions, right? The salt bridge is there so that, you know, the anode and cathode are neutral solutions, right? You can't get, I mean, you don't have a liquid solution that has some net positive or negative charges, right? These got to stay net neutral. Okay. You know what a galvanic or voltaic cell is, what the definition of that is? For that. Yes, so the one I have set up here is like a galvanic cell. Why is it a galvanic cell? Yeah, right. It has a positive cell potential. I think it's what kind of you getting that right. Right, which, as we'll talk about, show means that it is a spontaneous electrochemical reaction. An electrolytic cell, right, that's used for electrolysis, okay, is for some sort of non-spontaneous electrochemical reaction, okay, which will have a negative cell potential, okay, right. So electrolysis, for example, is often what's done to plate metals on the surface of something, right? You have a bunch of, you know, gold ions floating around in solution, right? You insert some sort of metal electrode in that solution. You then apply a potential to the solution to cause an electrochemical reaction to occur, right? And cause that gold ions to form gold solid, right? You can then plate gold onto, say, your electrode, right? Through this process of electrolysis, right? But to do that, to make that occur, typically you have to apply a potential, right? Apply a voltage. You got to put in energy for it to occur, right? And so it's not a spontaneous electrochemical reaction, right? So it's an electrolytic cell, okay? Which again, a galvanic cell is a spontaneous electrochemical reaction. Electrolytic is non-spontaneous, right? Then again, you have your anode and cathode, right? The anode is where the anions flow to, and it's where your oxidation reactions occur. And your cathode is where your cations from your salt bridge flow to, and where it's the reduction reaction occurs. We'll talk more about the next slide. But any questions are kind of about this definition, setup of these things? Yeah. right? Because we'll eventually just have problems talking about at the anode, there's this, cathode that, oxidation this, reduction that, galvanic this, blah, 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 right? So, not every problem you're going to see is going to have a nice, pretty picture like this to try to illustrate what's going on, right? So it's good to make sure we have an idea of what these different words mean and their significance in a problem. All right. Then we have, again, things like oxidation number. Remember what oxidation number is? That's trying to represent. Right. Oxidation number is essentially your effective charge on an atom, right? Not actually the actual charge, but it's sort of an electron counting keeping tool that we as chemists use to kind of represent, again, rough charges on different atoms, right? If everything was bonded ionic, right? Essentially, if you were to imagine every single molecule, every single thing was bonded ionically, right? These would then be kind of the rough charges we'd expect to see on these different atoms, right? Now, not everything's an ionic bond, so you don't actually see those charges, right? Those oxidation numbers, but that's what we use, and it's a useful tool for redox chemistry, right? Electrochemistry, because it allows us to kind of understand where the electrons are most likely flowing from and to, right? What atoms are the electrons getting taken from? What atoms are they getting added to? An oxidation reaction, what is that type of a reaction? What's occurring? Yeah, you're losing electrons, right? Oxidation reaction produces electrons, right? And the reduction reaction, you get electrons, right? Okay. And your overall electrochemical reaction, often we call a redox reaction, right? It's an oxidation plus reduction reaction occurring at the same time, right? It's a redox reaction. It's often what we'll call them, right? Right. As a reminder, your oxidizing agent is doing what itself? Is it being oxidized or is it being reduced? It's being reduced, right? Your oxidizing agent itself is being reduced. It's causing something else to be oxidized, right? Your oxidizing agent is causing something else to be oxidized, which means it itself has to be reduced. And then vice versa, right? Reducing agent is something that itself is being oxidized and causing something else to be reduced. Okay? Right? And then often we'll split up our redox reaction into half reactions of our oxidation reaction and a reduction reaction. Okay. And a redox couple is just the coupled redox reaction. Right? Questions about any of these definitions? And hopefully a lot of these things have been, what the heck? What? Okay, that was some weird formatting. All right, stay there. Nope. I don't know what I did, how I messed up something. All right, anyways. Okay. So then let's do some just quick oxidation number reviews, right? What is the oxidation number of sulfur S in the compound SO4 2-? It's going to be E here, positive 6, right? For those who don't remember kind of your rules, right? Your rules are your halides have a -1 oxidation number. Oxygen is -2, except in like hydrogen peroxide, right? Otherwise, oxygen is -2. Hydrogen is plus or -1, depending on what it's attached to. If it's attached to the metal, right, it's -1. If it's attached to a non-metal, it's going to be +1. Okay. And then besides that, all of the other oxidation numbers you get from summing up all the oxidation numbers summed up have to equal your charge, right? So in this compound, right, oxygen has a -2 oxidation number. So I get a total of -8. That's equal a total charge of -2. So the sulfur here has to be +6 in order for that to work out. Okay. Right, so in this molecule, oxygen's oxidation number is B -1, right? Hydrogen peroxide, so it's -1. or essentially you can think of it as the hydrogen oxidation number rule overwrites the oxygen one, right? Hydrogen having a charge of oxidation number of +1 or -1 is more important than oxygen having an oxidation number of -2, right? So if hydrogen has to be +1 in this case, then oxygen has to be -1 in this case, right? Yeah. All right. So again, if those things aren't familiar with you, just kind of review oxidation numbers, right? There's plenty of examples online. You can always look up to review those things. Not too important to review them for this class, but it doesn't hurt to at least have an idea of them, right? All right. So how many electrons are transferred for this half reaction when it is balanced? Small number of whole coefficients. Right, 2 electrons, right? Balance this. Oh, I thought I had the answer. No, but this right. You have 2 H pluses being formed. To balance the charge, I got to add 2 electrons, right? And so this balanced half reaction will be H2 going to 2H plus 2E minus. So there will be a total of 2 electrons being transferred. Okay. All right. Right, so here, right, how many electrons are being transferred? The following reaction is balanced with a small whole number of coefficients. Okay. Balance this electrochemical reaction. How many electrons are being transferred when you do so? So 1 here, the other 3. All right, so right in the half reaction for zinc, I am producing 2 electrons. In the half reaction for cesium, I am consuming 3 electrons, right? And so if I balance that to where I have, right, an equal number of electrons being produced and consumed, but I'm just leaving things in whole numbers, right? I don't want fractions of electrons and things like that, right? Then I need, right, the lowest multiplicative factor or something like that, right? That's what it's called, I forget. Right, 6, right? That I can have 3Zn plus 2Ce2 plus, forming 3Zn2 plus 2Ce solid, right? And that will balance the charges and have equal number of 6 electrons being consumed and produced in your balanced chemical reaction. So D here, 6 electrons is the total number of electrons that's being transferred in this balanced electrochemical reaction. Okay? You can also think of it, right? A balanced electrochemical reaction will have equal charges on both sides of the reaction, right? So I have +3 charge on the left side, +2 charge on the right. In order to balance the total number of charges, right, I need to multiply, right, my cesium by 2, by 3, so I get a +6 charge on both sides of the reaction, right? Which ends up meaning that there's 6 electrons being transferred. Okay. All right. So consider the following reduction: half reaction, or reactions, right? Write out the overall reaction as a sum of the oxidation and reduction reaction. And you can assume here, right, both these reactions are written as reduction reactions. You're going to assume only the second one is the actual reduction reaction. So the first reaction You want to write it as an oxidation reaction, so you got to flip that reaction. You want to have a final reaction. I mean, just the simplified final chemical reaction. Yep. Right, just the final balanced chemical reaction, once you flip the top one, right, is going to be, and then balance, you know, charges and things like that. If you add the reactions together, you want to make sure the number of electrons are equal. So you're going to multiply the top reaction by 2 and flip it. And so the final balanced chemical reaction after simplifying is just 2 H2 gas plus O2 gas forming 2 H2O liquid. Right? Okay. And here, just kind of, again, we had the electrochemical cell we're used to seeing, right? There are other types of electrochemical cells that can occur, right? Where you have, say, something like this, okay? You know, this is closer to what something like a battery is potentially composed of, right? Where you have 2 different kind of solutions within the same container. They're just separated by some semi-pure, like a porous membrane, right? Semi-permeable. Thank you. I'm almost like imperial or something like that. Like that's not right. Thank you. Yeah. Semi-permeable membrane. Okay. Right. That doesn't allow the molecules involved in the chemical reaction to flow between the membrane, right? But can allow something like, say, sodium or potassium or chloride or whatever, you know, your ions to maintain net charge neutrality with these solutions that flow between them. Okay. All right. And here, just a reminder of kind of this cell notation that may not be used to you in general chemistry. Right. So the typical notation here is we have the double vertical line, right? That is denoting kind of the salt bridge, the separation between the anode and the cathode. Okay. Right, on the left side of this double line is the anode, right, where your oxidation reaction's occurring. Right, the left side will always be anode oxidation, whether or not you have a spontaneous electrochemical reaction, a galvanic cell, or an electric cell, non-spontaneous redox reaction. Right, you always have the anode on the left, cathode on the right. Okay. Right, and then you have a single solid line to separate kind of the solution from the electrodes. Okay. Right, notice here at the cathode, right, the electrode is just solid platinum, right, isn't involved in the electrochemical reaction. It might catalyze the reaction, but it's mainly there as well to transfer those charges, right, carry the charges from one side to the other. Questions about kind of the cell notation, right? Right, so the overall chemical reaction not necessarily balanced. I think the balanced chemical reaction would be essentially Zn plus 2H plus forming Zn 2 plus H2 gas. It's going to be your balanced chemical reaction. Okay, right, based off of what's given here. Again, the left side is the oxidation reaction. So zinc goes to Zn2 plus. The right side's the reduction action. So H plus has got to go to H2. Questions? Again, like our discussions on chemical equilibrium, right? Some of this stuff, hopefully a lot of this stuff is kind of review and whatnot. Right, and so based off this, right, for that cell notation here, right, the physical anode electrode is what? Right, yeah, the anode, which is the oxidation reactions on the left, so it's zinc solid, right? All right, so any questions about kind of just some of this general concepts of electrochemistry, electrochemical cells, right, anodes, cathodes, oxidation numbers? All right. Let's talk about cell potentials, right? Right, and so again, for your cell potentials, we're interested in for redox reactions, kind of, a reduction reaction and an oxidation half reaction. Those things combining together form an overall chemical reaction. Okay, and often we'll write the half reactions, these redox reactions, and then write, say, their cell potentials, right, for those half reactions. Okay, and then here, just noting as well the fact that if you flip your reaction, notice that the cell potential, right, potential electrochemical reaction is just reverse in sign, right? So the same type of thing that occurs with enthalpy and entropy and things like that, right? You flip the chemical reaction, you're going to flip the sign of your overall cell potential. Right? Now, if you multiply your chemical reaction by some number, the cell potential is unchanged, okay? Because this cell potential or electromotive force, EMF, okay? So myself and other places use terms cell potential, electromotive force, okay? Both referring to the same thing, EMF, the electromotive force, the cell potential, and that itself is an intensive quantity, okay, right? So it does not matter how many, moles in total you transfer, things like that, right? That cell potential is constant, okay? Right? What changes based off the number of moles of electrons being transferred, okay, is not the cell potential, but say the work that's done by an electrochemical cell, right? Because that work that's being done is related to cell potential times the number of charges that have been transferred. Okay? But the cell potential itself is an intensive quantity. Okay? Think of it as, say, like a molar heat capacity or something like that, right? It's intensive, doesn't matter on the total amount you have. Okay? And again, by definition, a galvanic cell, okay, is a spontaneous cell that has an overall cell potential that's positive, okay? And you get the overall cell potential by just adding cell potential to the two half reactions, right? Now, in this way of doing things, right, where we define our cell potential by adding the cell potentials of our reactions, right, we need to know what the cell potentials of our half reactions are, but you can't measure those independently, right? Because again, I can't have just a oxidation or a reduction reaction occurring. Those electrons got to go somewhere, right? So if you got an oxidation reaction, something's going to get reduced because those electrons aren't just going to hang out in solution, right? If you have a reduction reaction, right, those electrons had to come from somewhere. They don't just come from thin air, right? And so we define some sort of standard. Okay, the standard is the hydrogen electrode. Sometimes the other common standard used is, I think, aluminum. Okay, aluminum redox reaction, if I recall. I don't know well enough the reasons why one standard is used over the other, but I mean, it might just be because, right, if you want to measure the cell potential of a half reaction, right, if you need to use one of the other half reactions as this reaction here, H2 gas or H2 plus going to H2 gas, right? Because this is defined as having a cell potential of 0, right? That the cell potential, the standard hydrogen electrode cell potential, assuming 1 molar concentrations, right, or 1 molal or whatever, right, 1 bar pressures of your gas, right, has by definition a cell potential of 0, right? We're just going to say this is equal to 0, right? We're just defining it as 0. So then if I do, right, some sort of electrochemical reaction, right, where 1/2 react this, so do I have, right, and let's say the other half reaction is zinc, right? So if I have this zinc half reaction occurring and then that hydrogen half reaction occurring in the other side of my electrode, or not electrode, my electrolytic cell, right? The overall cell potential I'll measure is going to be related with 0.76 volts. And then I can just directly assign that to the zinc half reaction because, again, right, by definition, the cell potential of the hydrogen half reaction is 0, right? So again, just kind of writing out some of these things, right? Overall cell potential, right, is just equal to the reduction cell potential plus oxidation cell potential, right? And if one of these reactions is the standard hydrogen electrode, right? If one of these reactions is, right, the H plus going to H2, right? That half reaction, right? That's defined as 0, right? And so if one of these guys is that, then my cell potential just equals the reduction or oxidation cell potential of the other half reaction, right? Depending on whether or not you're oxidizing or reducing H plus, right? So it kind of just depends on what's going on in the reaction, right? But, okay. And so that's how we measure these cell potentials for different half reactions, is we're measuring them all relative to the standard hydrogen electrode. Right? But again, there are some other standard electrodes that are used, and in papers they'll report, you know, this potential is measured relative to, say, the standard hydrogen electrode or the standard like aluminum electrode, right? And I think it's aluminum. And I think part of the reason for that is just then you don't have to deal with gases and crap like that, right? Standard hydrogen electrode uses hydrogen gas. You got to make sure you got 1 pressure of your gas, right? You got to have a pH of 0 solution, blah, 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 if you want that cell potential to be 0, right? If you don't want the cell potential to be 0, we'll talk about how the cell potential changes with changes in concentration. So you can still use this half reaction H plus going to H2, right? Not at 1 molar concentrations and 1 bar pressures, right? You can have non-molar and non-1 molar, non-1 bar pressure systems and still use this as your reference electrode. You just have to kind of modify some things, and we'll talk about that in a little bit, probably next time. pH of 0, I mean, pH of 0 is your concentration of H plus is 1 molar, right? Because the pH is the negative log of H plus concentration, right? Which if H plus concentration is equal to 1, right? Negative log of 1 is 0. So again, in practice, you don't actually do anything with like pH of 0 solution, right? You're never going to have that acidic of a solution, right? Okay. And so again, in practice, even when using the standard hydrogen electrode, you're going to have your cell potential is going to be related with that, say, reduction potential, and then there's going to be some terms here related RT and F ln of pH2 over the concentration of H plus or something like this, right? There'll be some kind of correction related with this, related with kind of the Nernst equation that we'll talk about that you hopefully have seen before, right? But you essentially, if you are using standard hydrogen electrode, but you have like a neutral solution, right? You need to plug in the fact the concentration of H plus is not 1, but instead 1 times 10 to the minus 7, right? You say your pressure of H2 is not equal to 1 bar, right? But something else, you got to plug that in as well and things like that, right? So you have to correct for these things. Okay. Again, it's something that's very often done, right? But again, in order to kind of avoid some of that stuff, often different reference electrodes are used. Again, I think it's like aluminum or maybe it's silver. I don't know. I forget. But I know there's another common standard electrode that things are defined relative to. And then in the literature, you just got to make sure that you know what is their reference, what is their standard. Yeah. Other questions about this? All right. So I have a half cell containing H plus ion, H2 gas, right? Set up with a combination of nickel, 2 plus, and nickel solid. Half cell. The voltage measured is 0.28 volts, and the electrons are determined to moving from the nickel electrode to the hydrogen half cell. Question is, what is the standard reduction cell potential for the Ni2 plus 2E minus going to Ni solid? You don't have any thoughts? Some C's. Right. So in the problem, right, we're told the electrons are moving from nickel, the nickel electrode, to the hydrogen side, right? Which means what is occurring at the nickel electrode? Oxidation reaction, right? So that oxidation reaction is occurring, and the potential of that oxidation reaction is positive 0.28 volts, right? Okay. And so the oxidation reaction has a cell potential of 0.28 volts, right? Because the reduction reaction is the hydrogen one, which defined is 0, right? And so the cell potential for the oxidation of nickel to nickel 2 plus is 0.28 volts. And so the reduction of nickel 2 plus to nickel solid is negative 0.28 volts. So D here is going to be a minus 0.28. Okay. That makes sense. I'm happy to draw it out and kind of show, right? But again, the idea here is you're being told that nickel is being oxidized in the overall cell. The overall cell has a positive cell potential of 0.28, which means that oxidation reaction has to have a positive cell potential of 0.28, and so the reduction has to be minus 0.28. All right. right? So again, the cell potential is measured in volts, right? It's related with kind of work that can be done, okay? Right? With the number of electrons being transferred across this potential, right, can give us some amount of work, okay? Right? And the larger that cell potential, the more work you can get out, okay? And the more spontaneous that reaction is going to be, because that cell potential is related with Gibbs free energy, okay? That question is not related with this. What happened? I didn't add that. I guess that was a point. Decided to be next. Right. Not the question I was expecting to see. All right. So it's not here. I mean, next time what we'll do is we will start talking about and describing and giving the relationship between free energy and the cell potential, and then giving the Nernst equation, which is how the cell potential changes with concentration in your system. Okay. We'll talk all about that, right? But yeah, so for today, I'm happy to go over some more example questions of, say, oxidation numbers, of getting balancing redox reactions. I'm not really going to have something where you need to try to balance a redox reaction that's in a basic solution. It's got a bunch of hydrogens, and you got to go through those like 12 steps to do it or whatever. I don't really care about that, right? It's the redox reactions we're going to be trying to balance are things like this one, right? Very simple, not dealing with acids and bases and waters and crap like that, right? All right. I'm happy to go over more examples of this stuff. Again, the idea, right? I didn't have it written in the slides, right? But we've essentially talked about it, right? But again, the overall cell potential is related with the reduction cell potential plus the oxidation half reaction cell potential, okay? Now, often what you'll see, another version of this equation is written as E cell equals E cathode minus E anode, right? We're assuming these are both reduction potentials, okay? Right, because often what you can look up, right, is some chart of your electrochemical reactions, right? Zn2 plus 2E minus going to Zn, right? Right, and then it will give you the standard reduction cell potential for that reaction, say minus 0.28, okay, and and a bunch of other reactions, right? H plus 2H plus 2E minus going to H2, right? Would have 0 reduction and so on and so forth, right? Right. And let's say this is 0.15. Right? You a bunch of different reduction cell potentials, right? And so this formula here, right, just uses the fact that at the anode you have the oxidation reaction, and the oxidation potential is just the negative of the reduction potential. So that's why there's like this minus anode here, is because it's just using the fact that the negative of the reduction potential is equal to the oxidation potential, right? And at the anode, you have the oxidation reaction occurring, okay? So often you potentially have seen this form as well presented, something like this, right? E cathode minus E anode, where again, it's just using the fact that the anode has the oxidation reaction. So you just flip the reduction potential and take the negative of that. And so that's why it's minus the reduction potential of the anode, since you're actually having the oxidation reaction occurring at the end, right? So both, that form and just, the reduction and oxidation cell potential added together, right? Both work and both are valid, right? It just kind of depends on how you want to use it, what you want to use, right? But the note, again, main thing to note for this version with the minus sign here is that both these potentials are reduction potentials. Okay, you have to use the reduction potentials for that equation to work. All right. Any questions? All right, so I guess then we will end there today and kind of early today. If there are no further questions, right? Again, I'm not in any huge rush. Try to finish this stuff. And today on this, and then again, next time we'll talk about the relationship between the cell potential and free energy. Are there any questions from those here on Zoom before I close the Zoom session? All two of you.